Another problem in 3 dimensions that can be solved in a kind of a similar fashion as the 3D particle in the box is the isotropic quantum mechanical simple harmonic oscillator. And again, like the particle in the box, we kind of play off of our one-dimensional solutions, and we lean on those very heavily in this case, so that we don't have to solve everything from scratch again. So let's take a look at what's meant by this. First, let's recall a little bit, because we're going to use these solutions to construct a 3-dimensional solution. And remember, for a 1D simple harmonic oscillator in quantum mechanics, we had to solve this one-dimensional time-independent Schrodinger equation. This function here is the potential energy for a simple harmonic oscillator. After a fair amount of effort, we actually found the normalized energy eigenstates were of this form, where we've defined some terms. Omega naught is k over m, here, square rooted. That's in here. The hn of chi are the Hermite polynomials. I've given an abbreviated table here, but your book has a more extended table. And chi is this dimensionless variable that we introduced here. So we had these solutions. They're nice normalized eigenstates, and they correspond to the energy eigenvalue that energy En is h bar omega naught n plus a half. The quantum number is n on both of these, and we found that it went from 0, 1, 2, 3, etc. So a non-negative integer. That means that the lowest possible energy state was the n equals 0, which was h bar omega times a half. Well, if we're clever, we can easily use these to obtain the 3D solution without doing a whole lot of additional work. For an isotropic Hooke's law potential in 3 dimensions, that's of this form. It only depends on how far you are, how much the spring has been stretched from the origin. And r is the distance from the origin, the stretch in the spring. We're assuming a spring that has 0 equilibrium length, and that's what really makes this the simple harmonic oscillation. As we've seen, we can always cast it into this form by appropriate change of coordinate system. K is the spring constant, and r, in terms of Cartesian coordinates, is x squared plus y squared plus z squared. So r squared is really, r is really the square root of this, but when you square it, r squared is x squared plus y squared plus z squared. Now in 3 dimensions, we've got this equation. Here's the time-independent Schrodinger equation. There's our potential, kinetic energy operator, a wave function in 3 dimensions, here, and the corresponding energy. And using Cartesian coordinates for the Laplacian, turns into this here, and psi. And now then, this is really where the clever part is. If you'll notice, I can group things a little bit differently. I'll take this x derivative of psi and group it with 1/2 k x squared times psi here. Likewise, this y derivative, I group it with the 1/2 k y squared, since they're all sums times psi. And then the z, likewise, group it with the 1/2 k z squared times psi. And now then I've kind of got it almost like looking like one-dimensional equations. Of course, this function psi is a function of x, y, and z. So we still have to do our separation of variable. We look for separable solutions. And I call them, in this case, that psi of x, y, and z is psi x, which is a function, name of the function, that's only a function of x. Psi y is a function only of y, and psi z is a function only of z. And I plug these into equation 1 up here. And you'll notice that this first term here this only operates on psi x, so I can pull out the psi y and psi z. And this would have all three of these, but I can still pull out the yz and yy. And so that first term becomes this. But now everything in the brackets is only a function of x. I do a similar thing for this piece. Now I can pull out psi x and psi z. And I'm left with something that depends only on y variables. And then similarly, this last one, I can pull out the psi x, psi y. And I'm left with a term in brackets that only depends on z. And then I divide through by the full wave function, so I divide the whole equation through by psi x, psi y, psi z. And pretty obviously, when I divide out by this, I'll get 1 over psi x times this x term, 1 over psi y times this y equation, and 1 over psi z is equal to a constant. And now then, I do the same trick as before, separation of variables, but what it boils down to, if these are a function of x plus a function of y only plus a function of z only can add up to a constant, the only way that can happen is if this first term here is equal to some constant. I called it E1, and that gives me this first equation. This one must be a constant, which I called E2. And so that gives me this second equation. And then finally this third term, E3, which gives me this third equation. And then, of course, E has to be the sum of E1 plus E2 plus E3. So you can get three equations. And you'll notice each one of these is just a harmonic oscillator equation in one dimension. Well, they're all 1D simple harmonic oscillator equations, and we can use our previous solution in each direction. The only thing we have to be a little bit careful of is we need to use a different index, a different integer for each one. So I used n1 in the x, n2 in the y, n3 in the z. And these arguments need to be the dimensionless variable in the x direction, the dimensionless variable in the y, and the dimensionless variable in the z. So we get those one-dimensional equations, and we know what the energy levels are for these. E1 is En1. It's just h bar omega naught to n1 plus a half. E2 is h bar omega naught n2 plus a half. E3 for all these one-dimensional oscillators in each direction. So each direction separates out nicely in the case of an isotropic harmonic oscillator. The integers n1, n2, and 3 are non-negative, so they start at 0 and run on 1, 2, 3. But they can be varied independently of one another. They just have to be chosen from that set. And so that gives us the total energy as a sum of these. And if I plug these into here for E1, E2, and E3, and then collect terms, I can pull out a common factor of h bar omega naught. And then I've got n1 plus n2 plus n3. And then 1 half plus 1 half plus 1 half, which is 3 halves. So the energy levels for the isotropic simple harmonic oscillator in quantum mechanics turns into this expression. Depends on three quantum numbers, n1, n2, and n3. The wave function, total wave function, is just the product of those. But again, I can choose different n's for each one, for psi x, psi y, and psi z. And I've got the eigenstates, characterized by 3 quantum numbers, and I've got the corresponding eigenvalues of energy. If you look at these and pull everything together, you have the ground state. The lowest possible energy is when n1, n2, and n3 are all 0, in which case the energy is h bar omega naught times 3 halves. And there's only one way to do that. That's psi 0, 0, 0. And that's the ground state, so its degeneracy is 1. The first excited state, the next available energy really, is if 2 of these are 0 and 1 is 1, and then you'll get the energy is going to be 1 plus 3 halves or 5 halves, so you get 5 halves h bar omega for the first excited state. And as I said, the 1 can be either at N1 or at N2 or at N3, and the others have to be 0 for that first excited state. The second excited state will have to have any combination in which the quantum numbers add up to be 2. In that case, if I get a 1 and a 1 and a 0, then this adds up to be 2, which is 4 halves, and I add that to 3, so I'll get 7 halves. And so the second excited state has an energy level, which I would call E2 for the second excited, is h bar omega naught plus 7 halves. But how do I get that? Well, there's multiple ways you can get it. You can get a 0 in the first term, a 1 to 1. You can get a 0 in the second, a 1 and a 1, or 0 in the third, so all of these add up to be 2. Or you can get a 2 and 2 zeros, but the 2 could be at either N1, N2, or N3. So if you look at all of those, you've got 1, 2, 3, 4, 5, 6 ways to get this energy, 7 halves h bar omega naught. So the degeneracy is 6 in this particular case. Well, you can continue on. You get more and more states, as you might imagine, as you go up to higher energies, and they proliferate. The degeneracy begins to increase. In addition, another thing that I should probably point out, if you look at the difference in energy between any 2 adjacent states, it's just h bar omega naught. So 5 halves, 7 halves, 3 halves, 5 halves. So the difference between the ground state and the first excited state is h bar omega naught. Between the first excited state and the second excited state, h bar omega naught. And so the energy levels are still separated by h bar omega naught, and they're all equally spaced. Well, that is a quick presentation on the simple harmonic oscillator. And again, we tried not to reinvent the wheel, but to use what we knew about one dimension to solve the equation for the simple harmonic oscillator in 3 dimensions.